Hello everyone, today we will learn about infinite series and some related theorems. Infinite series. A series is the sum of the terms of a sequence. Let un be a sequence, then the sum u1 plus u2 plus u3 plus plus un up to infinity of all the terms is called an infinite series and is denoted by sigma n is equal to 1 to infinite un, or by simply sigma un. To the given sequence un, which underlines the infinite series referred to above, we associate another sequence Sn defined as follows: Sn is equal to u1 plus u2 plus un plus up to un. That is, Sn denotes the sum of the first n terms of the series. Thus, Sn denotes the sum of the first n terms of the infinite series sigma un. The sequence Sn is said to be sequence of partial sums of the series sigma un. Definitions: the infinite series sigma un is said to be convergent if the sequence Sn of its partial sums is convergent. If limit n tends to infinite Sn is equal to S, then S is called the sum of the series sigma un, and we write S is equal to sigma un. The series sigma un is said to be divergent if the sequence Sn of partial sums of sigma un is divergent. The series sigma un is said to oscillate if the sequence Sn of partial sums of sigma un oscillates. Example 1. Consider the series sigma n equal to 1 to infinite 1 by n into n plus 1, that is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 up to infinite. In this case, un is equal to nth term of the series is equal to this 1 by n into n plus 1, which gives 1 by n minus 1 by n plus 1. Therefore, for n is equal to 1, u1 is equal to 1 minus half. For u is equal to 2, u2 is equal to half minus 1/3. u3 is equal to 1 by 3 minus 1 by 4. In this way, last term is un equal to 1 by n minus 1 by n plus 1. Now, Sn is equal to sum of the first n terms of the series. Therefore, Sn is equal to u1 plus u2 plus u3 plus un is equal to 1 minus 1 by n plus 1. Therefore, limit n tends to infinity Sn is equal to limit n tends to infinity 1 minus 1 by n plus 1 is equal to 1. Therefore, the sequence of partial sums Sn converges to 1. Therefore, sigma n is convergent with sum 1. Example 2. Consider the series sigma n is equal to 1 to infinite n square, that is, for n is equal to 1, this is 1, n equal to 2, this is 4, and in this way series becomes 1 plus 4 plus 9 plus 16 plus 25 up to infinity. In this case, un is equal to nth term of the series is equal to n square, and Sn is equal to u1 plus u2 plus u3 plus un is equal to 1 square plus 2 square plus 3 square up to n square. Therefore, Sn is equal to n into n plus 1 into twice n plus 1 by 6, and taking limit on both sides, we have limit n tends to infinity. Sn is equal to limit n tends to infinity n into n plus 1 into twice n plus 1 by 6 is equal to infinite. So Sn diverges to infinity. Therefore, n is equal to 1 to infinity. Therefore, sigma n is equal to 1 to infinite n square is divergent series. Example 3. Consider the series sigma n is equal to 1 to infinite minus 1 raised to the power n minus 1. Here un is equal to minus 1 raised to the power n minus 1, and s1 is equal to 1, s2 is equal to 1 minus 1, that is u1 plus u2 is equal to 1 minus 1 is equal to 0, s3 is equal to u1 plus u2 plus u3 is equal to 1 minus 1 plus 1 is equal to 1 dot dot dot. Thus Sn is equal to 1 0 1 0, which oscillates. Therefore, the given series is oscillatory. Theorem. Necessary condition. If the series sigma n is equal to 1 to infinite un converges, then limit n tends to infinity un is equal to 0. Proof. Let Sn is equal to u1 plus u2 plus u3 plus up to un, and limit n tends to infinity Sn is equal to s, so that limit n tends to infinity Sn minus 1 is equal to s. Now we have un is equal to Sn minus Sn minus 1, implies that limit n tends to infinite un is equal to limit n tends to infinite Sn minus 1, which implies that limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1 is equal to s minus s is equal to 0, because limit n tends to infinity Sn is equal to s and limit n tends to infinity Sn minus 1 is equal to s. So, their difference gives 0. Therefore, the series sigma un converges if the series sigma n equal to 1 to infinity un converges, then limit n tends to infinity un is equal to 0. But the converse of the above theorem is not true. That is, if limit n tends to infinity un is equal to 0, then it does not mean that the series is convergent. Consider the series 1 by under root 2 plus 1 by under root 3 plus up to 1 by under root n plus up to infinity. Here un is equal to under root 1 by n, and limit n tends to infinity un is equal to limit n tends to infinity 1 by under root n is equal to 0. But the series does not converge as shown below. Here sequence of partial sums of the series Sn is equal to 1 plus 1 by root 2 plus 1 by root 3 plus up to 1 by under root n, which is greater than 1 by under root n plus 1 by under root n plus up to 1 by under root n, which gives n by under root n is equal to under root n. Thus, Sn is greater than a square root of n, which tends to infinity as n tends to infinity. So, the series is divergent. Corollary: if limit n tends to infinite even is not equal to 0, then the series cannot converge. Example 4. Show that the series under root 1 by 4 plus under root 2 by 6 plus up to under root n by 2 times n plus 1 plus up to infinity does not converge. Here un is equal to under root n by 2 times n plus 1 is equal to 1 by under root 2 into under root 1 by 1 plus 1 by n, which implies that limit n tends to infinity un is equal to limit n tends to infinity 1 by under root 2 a square root of 1 by 1 plus 1 by n, which gives is equal to 1 by under root 2. Implies that limit n tends to infinity un is equal to 1 by root 2, which is not equal to 0. Therefore, the series does not converge. Similarly, we can show that sigma n is equal to 1 to infinite cos 1 by n square is not convergent. Similarly, we can show that sigma n equal to 1 to infinite cos 1 by n square is not convergent, that is divergent, because here un is equal to cos 1 by n square and limiting value of this is equal to 1, which is not equal to 0. Therefore, this series is divergent. Cauchy's general principle of convergence for series. Theorem: a necessary and sufficient condition for a series sigma un to converge is that to each epsilon positive there exists a positive integer m such that modulus um plus 1 plus um plus n up to plus un less than epsilon for all n is greater than m. Proof: let Sn be the sequence of partial sums of the series sigma un. Now we have sigma un converges if and only if Sn converges. If and only if to each epsilon positive there exists a positive integer m such that modulus Sn minus Sm less than epsilon for all n is greater than m by Cauchy's general principle of convergence for sequences. If and only if um plus 1 plus um plus 2 plus up to un is less than epsilon for all n greater than m. Example 5. Show that the series sigma 1 by n is equal to 1 plus half plus 1/3 plus 1 by n does not converge. Proof: if possible, let the series converge, then for epsilon is equal to 1 by 4, by Cauchy's general principle of convergence, we can find a positive integer m such that 1 by m plus 1 plus 1 by m plus 2 plus up to 1 by n is less than 1 by 4 for all n is greater than or equal to m, which is equation number 1. Now, taking n is equal to twice m, we have 1 by m plus 1 plus 1 by m plus 2 plus 1 by n is equal to 1 by m plus 1 plus 1 by m plus 2 plus 1 by twice m is greater than 1 by twice m plus 1 by twice m plus up to 1 by twice m, which is equal to m by 2 times m is equal to half. Thus 1 by m plus 1 plus 1 by m plus 2 plus 1 by n is greater than half for all n greater than m, which is contradiction to our equations 1. Therefore, the given series is not convergent. Positive term series. Series with non-negative terms are the simplest and the most important type of series one comes across. The simplicity arises mainly from the fact that the sequence of its partial sums is monotonic increasing. Let sigma un be an infinite series with positive terms and Sn the sequence of its partial sums, so that Sn is equal to u1 plus u2 plus up to un, which is greater than or equal to 0 for all n belongs to n, because u1, u2, un are all non-negative terms. Therefore, this is greater than or equal to 0. So, Sn plus 1 minus Sn is equal to un plus 1 greater than or equal to 0, implies that Sn plus 1 is greater than or equal to Sn for all n belongs to n. Thus, the sequence Sn of partial sums of a series of positive terms is a monotonic sequence. Theorem 1. A necessary and sufficient condition for the convergence of a positive term series sigma n equal to 1 to infinite un is that the sequence Sn of the partial sums of the series defined by Sn is equal to u1 plus u2 plus 2 un is bounded. We know that the sequence of its partial sums of a positive term series is a monotonic increasing sequence, and a monotonic increasing sequence converges if and only if it is bounded above. Therefore, it follows that a positive term series converges if and only if its sequence of partial sums is bounded above. That is, here this is bounded above. Corollary. A series sigma un of positive terms converges if and only if there exists a number k such that u1 plus u2 plus un is less than k for all n belongs to n. This is the consequence of this theorem, because we know that this series convergent if and only if its partial sums is bounded above. So, bounded above means there exists a positive integer k such that its partial sum is less than k. Theorem 2. If a series of positive terms is divergent, a series of positive terms is divergent if each term after a fixed stage is greater than some fixed positive number. Theorem 3. If each term of a series sigma un of positive terms does not exceed the corresponding term of a convergent series sigma vn of positive terms, then sigma un is convergent. If each term of a series sigma n of positive terms exceed or equals the corresponding term of a divergent series sigma vn of positive terms, then sigma un is divergent. That is, if each term of this series is greater than or equal to corresponding terms of the series Vn, sigma Vn, which is divergent, then sigma un is divergent. If sigma un is a series of positive terms such that limit n tends to infinite un is not equal to 0, then sigma un diverges. If sigma un and sigma vn are two convergent series, then sigma un plus minus vn are also convergent. That is, sum of two convergent series also convergent, and difference of two convergent series also convergent. Example 6. Show that the series sigma n equal to 1 to infinite 1 by n raised to the power 1 by n diverges. Here un is equal to 1 by n raised to the power 1 by n. Taking logarithm both sides, we have log un is equal to 1 by n log of 1 by n, which gives minus of log n by n. Taking limit n tends to infinity on both sides, we have limit n tends to infinity log un is equal to minus of log n tends to infinity log n by n, which is of the form infinite by infinite. Then by L'Hospital's rule, we have 1 by n by 1. This is the differentiation of numerator and denominator. Thus, limit n tends to infinity log un is equal to 0, which implies that log of n tends to infinity limit un is equal to 0, implies that limit n tends to infinity un is equal to e raised to the power 0 is equal to 1, which is not equal to 0. Therefore, the necessary condition for convergence of a series does not satisfy, and hence the given series is divergent. Example 7. Show that the series half plus 2/3 plus 3 by 4 is not convergent. Here un is equal to n by n plus 1, therefore n tends to infinite, un is equal to limit n tends to infinite n by n plus 1 is equal to 1, which is not equal to 0. Since limit n tends to infinite un is not equal to 0, therefore the series is not convergent and the given series is divergent. Thank you very much for watching this video. Please don't forget to subscribe my channel. Please like, share and comment. Please press the bell icon to get notifications.